Is it on?
Uh,
Yeah,
Yeah.
we're live. Okay. So let me introduce Christian. So it's my pleasure to introduce you, Christian, which is my colleague at Oracle Labs. He's the Truffle lead, so he leads the development of Truffle. And actually, I'm interested about the story of Truffle. Like, I know your thesis was on the Truffle DSL, if I'm not
Yes.
confused, but like, did you create Truffle or how did it come to be?
So I was lucky to be there. So I actually did my bachelor thesis with Thomas Rüttinger, who is the lead of the Graviem project. And I basically started doing my studies at JKU, and I was in his class, in his software development 2 class, and it seems like he liked me as a student, so he asked me to being tutor for him. And then after being tutor, he asked me, "Oh, where do you do your bachelor thesis?" And then I did my bachelor thesis, and my bachelor thesis was about um, bytecode interpreters in Java. So basically, this was the first version of Espresso. Very, very rough. We're using much of Hotspot for the meta stuff. And so I did a bytecode. So just as a proof of concept, can you write something like low-level bytecode interpreters in Java and interface with the VM properly? And that was pretty successful. And that also was kind of this was before Truffle existed. So then I started getting a contract and was working at the institute directly, also working on my master thesis, which was Truffle DSL in the end. But I actually started with Java on Truffle next to GraalJS, JavaScript on Truffle. Back in the day, and I was working with Thomas developing the framework, but he did the big stuff, the fundamental concepts, and I tried to keep up back then. But today I think I understood it reasonably well, but it took me a while.
All right. Well, this will be a talk about Truffle, so students will be able to learn all about that, and in particular, like the compilation concepts.
Right.
And it's all yours.
Thank you very much.
Yes, maybe before we start, if you have any question during the talk, feel free to put them in the chat, and we might do a few breaks where we tackle all the questions that are there. Okay.
Yeah. Also, feel free to unmute and just ask a question. I think as long as if it works, we're not getting too much traffic. Okay, so the topic today is going to be dynamic meta compilation with Truffle, as already announced. I'm already introduced, so I don't need to say much. My name is Christian Humer. I'm industry researcher, VM engineer, actually in Oracle Labs Zurich, but currently I'm in Austria because I'm originating from Austria, and it's weird times. And I'm working on Graviem for 8 years. Over the time, I worked on the R language, worked on the JavaScript language. Already talked about that I did the Truffle DSL framework, which was my master thesis, which I'm still maintaining. But today, my primary role is pushing the Truffle framework in the right directions for the future. There's also my Twitter handle if you want to follow me along. So what to expect today? So we are going to start with some basics, interpretation versus compilation, and we'll probably go rather quickly over them. What is manual compilation? What is then meant by meta compilation? Then one of a particular meta compilation technique, the Futamura projections, we will discuss in a little bit more detail. And then we will go, I will introduce to you Graviem and Truffle and how the whole system is situated. And then we'll tell you step by step how Truffle does the meta compilation steps. And then we will take the meta JIT compilation of Truffle to the next level and making it a dynamic compiler. I will explain what that means in a second to introduce speculation and optimization. And then I will talk a little bit about the motivations we have behind Graviem, why we built this. And so basically we want to build a polyglot VM, more that later. And then I will tell you how we actually use Truffle to compose languages and tools, compile them together into a single compilation unit. And in order to spice things up a little, I prepared 4 demos. So hopefully they all going to work. The demo gods are with me. So the first 2 demos are actually, you can actually follow yourself. But if you want to do that, you can download under this link, this PE demo, clone the Git repository. The README contains some instructions on how to download Graviem, run the PE demo, and also where to find Idea Graph Visualizer, which you're going to need later on. it's not required. So if you just want to listen to it, it's fine too. Wait, oh, that's the wrong direction. All right. So the first thing I want to talk about is pure compilation. So in pure compilation, typically what you have is you have a source program, a program written by a user. You pass it on to a compiler. You get the target program. And the target program in high-level languages is often translated to machine code or object code. And then later on, you take the target program, give it the application arguments, and you get the output. I think everyone knows how this works. Right. So the target program is really the locus of control. So the generated machine code is important. And then next to that, there exists pure interpretation. In interpretation, you have a source program and an input arguments, and you pass both of them directly to the interpreter. The interpreter takes the source program, parses it, and executes it using another program, and then executes the program using the inputs that were provided. So the interpreter stays around for the execution of a program, whereas the compiler gets really removed entirely from the target program typically. And in pure interpretation, we really only interpret the input code. So an interpreter typically also implements something like a virtual machine, language virtual machine, that keeps metadata around, like classes or bytecodes and things like that in order to do the interpretation. Whereas in pure compilation, you can get rid of most of the metadata, but that's also dependent on the languages. Interpretation typically gives you more flexibility, so better error messages and debuggability, but also compiled languages can get really close.
Do you have an example of metadata that's kept around by an interpreter?
Yeah, so maybe just explain this using Java bytecodes, right? Java is really a mix of both, right? You kind of have a pure compilation step in the beginning where you have the Java source code. You pass it on to the compiler and you get Java bytecodes out of it. And then later on, if you disable compilation on the Java VM, then you only have an interpreter that takes the Java bytecodes and executes them. And the metadata you would contain in the interpreter would be the class structure, the methods defined, the names, the symbols, all that. And of course, also the optimized code if we have a compiler involved, which is the next thing I want to go. Did this answer your question?
Yes, that's perfect. And they've also seen the Java bytecodes, which would make sense.
Yeah. So the first thing I want to explain is just-in-time compilation. So this takes basically the interpreter idea and adds a new compiler, basically mixes both concepts. So what the assumption just-in-time compiled system uses is whatever was executed in the past will be executed frequently, in the future again. So it's worth spending some time to optimize at runtime. So this basically means that you have a function, it's called very often, then at some point the interpreter decides to offload it to a compiler, compile it, and then typically the code stays in the compile code in a pure just-in-time compiled manner. So this is typically fairly easy to implement because you basically jump from the interpreter to the compiler and from the compiled code back to the interpreter only at function call boundaries. But where things come a little bit more interesting, which is actually a subcategory of just-in-time compilation, which I call dynamic compilation. Some people refer to dynamic compilation already as just-in-time compilation, but I typically make a difference, disaggregate them. Where you have a source program input, an interpreter, and the output. But now we basically have a speculative compiler in there that not just can compile something and then run in compiled mode, but it also can jump back to the interpreter and do a step called de-optimization, where you discard the compiled machine code or and go back to the interpreter. And this is typically a very complex step because you need to take the optimized code. The optimized code typically made a lot of assumptions in the code and optimized it in a way that that is efficient to execute. But then if you go back to the interpreter, you need to undo all these optimizations and basically reconstruct the interpreter stack and so on. So this is a quite an involved step, but it's really very powerful. So you can do what you in regular just-in-time compilation, you assume what was executed frequently in the past will be executed in the future. But in dynamic compilation, you can also say whatever types, structures, and data inputs I got in the past will also happen in the future. So you kind of record, we call this profiling, the kinds of data structures and data that you observed in the program, and then you optimize the interpreter code, the code for this input data. So the interpreter basically passes this, as we call it, profiling data on, and then the compiler can do speculative assumptions in the optimized code and produce faster code. Again, I already mentioned that if some people say JIT compilation, they often mean dynamic compilation, so the line between those two is a little bit blurry. In this talk, I will talk mostly about dynamic compilation. So the next thing is, what is manual JIT compilation? So the manual JIT compilation is really where you write the interpreter yourself and you also write the compiler yourself. So this typically means that you need to implement the desired language twice, once for the interpreter and once for the compiler. As you might imagine, these two components that are developed separately, so they might become out of sync, and then hence there is the possibility that these two things come out of sync. And for example, the compiler produces slightly different behavior than the interpreter, or the interpreter is different than the compiler. And so there is this idea to use meta JIT compilation for this, which is kind of say meta means it's generated derived from something, right? So what is regularly done is that you manually write the interpreter, and then you derive the compiler from the interpreter. So this way, these two components cannot become out of sync, and it's also much easier to do. In the one direction, generating a compiler from the interpreter is called is typically called Futamura projections. I don't know of another theoretical concept that allows you to do this, so there might be one. I don't know. But so this is the one that we are going to use for this talk of this lecture today. Important thing is, so you could think of this, so we have one meta step here, right? We have a manual interpreter and we generate the compiler out of it. But you could also, for example, say, I also want to generate my interpreter, right? Then you basically have some abstract specification of your interpreter, and you would generate a meta interpreter, and then you would have a meta compiler, if you want to say so. But we will not go there today. We actually have a fun research project around this ongoing at the moment to try to optimize a meta interpreter in Truffle. All right. Okay, this would be a good point for questions. Anything in chat already?
Nothing in the chat. Anyone has got a question? I think so far we've actually covered something fairly similar in the course.
Right.
We didn't do the distinction between JIT and dynamic compilation, but I did speak about C#, which tends to JIT everything, and Java, which uses a profile.
Right, but I think they also have some basic profiles in C#. But I mean, I know the line between those two is really blurry. It's really hard to say when something. It also doesn't matter. It's just a terminology question, right? Okay, then I will go on with Futamura projections, which is actually a pretty old idea. It's 1971. There are some papers after that, so way before I was born. And Yoshihiko Futamura investigated the relationship of semantics of programming languages and an external compiler. And he was the one who discovered that you can take the evaluation procedure, which we call today interpreter, and instead of conventional approaches where you write the compiler, you can generate, translate that interpreter to a compiler. And first, so the paper was originally called Partial Evaluation of a Computation Process, an approach to a compiler. So we also need to explain partial evaluation. And partial evaluation, you can think of a program. I mean, this is a very common optimization technique that actually many compilers can do. But if you're familiar with some optimization process in compiler, partial evaluation is kind of constant propagation and inlining on steroids. So what you do here is you take a program and you have some known static parameters to that program. And you pass it on to a partial evaluator, and it gives you a program that is specialized for the static parameters. So this is again a step before any execution happens. So for example, think of a function that has two parameters, right? The first one is some dynamic input data, and the second one is some static parameter. You pass it on to the partial evaluator, you get a new function with a single parameter that only takes the dynamic parameter. And as you can imagine, the partial evaluator can do optimizations and fold certain things in the program to produce this specialized program. So now a concrete application of partial evaluation is the first Futamura projection. And the first Futamura projection takes as input the interpreter of a program, so the generic interpreter of a program. As static input, you also get the source program. What this typically means, the ASTs and the data structures that you have already parsed. You pass it on to the partial evaluator, and that produces you a specialized program, basically an interpreter that can only execute the source program. And what is an interpreter that can only execute the source program? It is the program executable, right? That's just a different term to understand this. So in literature, it's called partial evaluation of an return-given source code yielding an executable. And this is really the thing where we're going to dive a little bit more in today. So we're going to go step by step what the partial evaluator does in Truffle to achieve this, and then it will also become much clearer how this optimization follows naturally from partial evaluation. So the second one becomes a little bit more meta. There's a second Futamura projection. This is where you basically have the partial evaluator instead of the interpreter that you pass to the partial evaluator again. So you pass itself to the interpreter, but a static input, you give it the interpreter itself. So the generic code of the interpreter. And what you get if you have a partial evaluator for a particular interpreter is basically you get a specialized compiler. So what is really important here to understand is that you need to understand the partial evaluator itself as an interpreter, because in the previous example we partial evaluated the interpreter, but now we instead of the interpreter we use the partial evaluator itself. So so it is kind of writing a language, so treating the partial evaluator itself as a compilable language. So this is the second thing. And after you produce the specialized compiler, you would then in a second step, so you would have first when you compile your language implementation, you would create the specialized compiler in your image, and then at runtime you would take the source program, hand it on to the specialized compiler, and that will produce fast program executables to you. So also want to say that we are not yet using the second Photomura projection in Truffle. We only have a generic partial evaluator, so we cannot partial evaluate the partial evaluator yet in Truffle, but we have an ongoing PhD thesis that explores this, and there is already some promising results. So there is also a third Futamura projection and actually a fourth Futamura projections, but they are more interesting as a theoretical concept, so they are not really interesting or practical to use, I think. At least I don't know how. So what you do there is, you might have guessed now, you basically take a partial evaluator as the interpreter, similar to the second Futamura projection, but now you pass the partial evaluator as the static input to the partial evaluator, which yields another compiler generator, or if you interpret it concretely, you could also say it is the same partial evaluator that comes as a result. So this is really just a theoretical thing because you want to prove certain properties of your partial evaluator. For example, if the partial evaluator, the left side partial evaluator, is the same as the output partial evaluator, then you can say this is actually Jones optimal. And Jones optimal is just I think Jones developed this term, that's why it's named after him. But it's actually not very hard to do. To really have a partial evaluator that doesn't add any additional. So what it means if your partial evaluator partial evaluates to itself is that you really don't add any additional overhead to the program, right? So you really can say now the program optimized fully away. So the meta generation is perfect. And actually I was lucky to be at PEPM 2017 in Lisbon, where Pausberg actually presented his work there, where he proved that his partial he actually had a formal proof where for his partial evaluator to be Jones optimal, which was fun. So if you're interested in really diving into the theoretical aspects of this, I invite you to follow this link and read this paper. It's not an easy read, so it will take some time. Right. One really, really fun thing that actually happens if you have a program that produces itself, that is also called a quine, right? And so you could say a Jones optimal partial evaluator is a quine, and then in the preparation, I remember that there is this fun language Urobos quine thing on GitHub, and it's actually fun to go there. So what it happens is basically it took this idea of a program that produces itself to the extreme. So they built a program that produced a program of the next language, and then gone through 128 languages until it produced itself again, right? So, this is actually fun to explore if you have some free time. The Quine Relay GitHub project, they claim to have them all runnable if you check that out. So you just need to install a few dependencies here. And then you can take it to the extreme, and then you just run the Ruby program that produces the RS program. I think, is that Rust? I don't know.
Yes, it's Rust.
Yeah. And then you go to Scala, and I don't know how they ordered this actually, probably it was not so easy to do between few languages. But that is really a fun exercise.
I wonder if maybe you can start at any point. Like they give you all the intermediary step and you can just pick anyone and start. I guess you should be able to do that.
I think you should be able to do that, but they would need to provide the intermediate steps, right? So what is the thing they... So
they start with Ruby, of course.
Sure. Do they have any other... No, I think they only have the Ruby files here.
Okay, interesting.
So you need to generate them yourself, the intermediate steps. Well, it's easy to maintain, right? The other stuff is just generated, right? So anyway, fun little, if you want, if you're locked down and you don't know what to do, this is, I think, a fun exercise. Also, if you want to mess up your machine, you probably will get a lot of problems if you install all of this. All right. So this is, of course, not the real thing. This is just some work of art.
I see it's actually developed by this guy that is, I think, a core Ruby developer. So that does explain something.
That's why he started with Ruby. All right. All right. Okay. So which brings me to actually our work, which is a paper we published, I think, a few years back.
Christian, we still see the the browser. Okay.
I see. So which we call practical partial evaluation. So where we basically take the idea of the first Futamura projections to implement in modern dynamic language runtimes, and we also want to achieve high performance. In this paper, really, we explain the fundamental building blocks that you need to implement dynamic languages. There is actually a little bit more than just metacompilation that you need for that, like stack introspection, and we describe all of that in the paper. But today we're going to focus on the compilation aspects of it. There's actually also so if you go to the website, we have like a lot of publications over the last years. We also have some recent ones to all aspects of the system. Yeah. So if you want to read up on this, there's lots of material here. And don't forget. Right. So let me introduce Graviem very quickly. So Graviem is basically a JDK, a Java JDK added with the Graal compiler. Graal is a just-in-time Java compiler. Here there is no partial evaluation yet, right? So this is just using Graal compiler as a replacement for the last year compiler in Hotspot as a dynamic compiler. So the idea is to run Java applications faster and to do more compiler optimizations there. And one interesting aspect of the Graal compiler is that it's actually written in Java itself. So it's kind of self-hosting. It's a meta-circular compiler, you can call it. Yeah, and that works pretty well. You get a speed up for Java applications, but that is not very special. So the ahead of time compilation for Java is something that is rather revolutionary. We basically take a Java program and you compile it ahead of time to standalone binaries that require low footprint. At the time of microservices, this got really popular, and this is actually an aspect we also use for the next part, which is the high performance polygon VM aspect, the Truffle part, where we use metacompilation to implement dynamic languages. And the interpreters that we write are also written in Java with Truffle. And we use also the ahead of time compilation technique to get rid of the Java overhead that typically was the problem when you wanted to do system software in Java. But with this AOT compilation step, we can actually remove the metadata needed for the Java execution. So it is really, it's a really valid choice to use Java over C++ to implement your language runtime.
So you mentioned microservices. And, to explain why it's interesting there is that this is when you deploy your services in the cloud, and often you also want to spin new instances on demand. And so it's important that it goes fast. And one of the issues with, let's call it normal Java, is that you need to boot up the VM, and that does take a little bit of time before you can run the program. So if you compile it to native image, so to native code, it starts much faster, which is nice in the cloud.
Yes, I think this is also known as serverless, where basically you turn down your application, then restart it when you need it. But I think another important aspect of it is that you actually reduce the memory consumption of it. So it is easier to scale multiple instances of those Java programs. Yeah, but this is actually another big reason why people use that. Yeah, but so this EOT component, which we call native image, is really used also for this Truffle aspect. And this is actually also where the project originated from. So this the EOT compilation for Java was actually built for Truffle in order to take our runtimes and put them into the database, because the Oracle database is a very restricted space where you cannot run everything, right? So, and for sure not the Java program, right? Because that requires threads and all that stuff, which is not allowed in the database, and not directly allowed in the database. And this was the way this was developed. So first, the native image component was actually designed for Truffle to bring it into the database, and now we use it also for regular Java applications, and we also use it for standalone images when we deploy our languages.
I didn't know that. That's interesting.
Yeah. And that's why the native image component also has a capability to include the Graal compiler itself, so we can do the dynamic compilation in those images that we produce. Okay, so system overview, we have the Java VM underneath, then we have the Graal compiler, we have our JVM host languages that run on it, and then we have the polyglot Truffle runtime that uses the Graal compiler and applies partial evaluation to apply partial evaluation. Then we have our direct language implementations like R, JavaScript, Python, or Ruby. These are really just ESC interpreters that get that use Metacompilation to become fast. And then we have another indirection on top to run native languages. For example, we can interpret LLVM bytecode with a project called Sulong, where you basically configure your C compile in a special way to output LLVM bytecode, and then we can interpret that. We also have an interpreter for WebAssembly bytecode that works in a similar way. And I think important to note is that we actually support both styles of interpreters. We support bytecode interpreters, where you basically have a byte array where you dispatch on bytes, and we support EST interpreters, where you really build an EST data structure and then you traverse the EST to execute the program. Both of these things are currently implemented. We're not fully decided what is going to be the final version. So for some languages, it's just natural to implement them as an EST interpreter. But I think for footprint reasons, because we need a lot of allocations and runtime overhead, we might need to go to a bytecode-based approach for some of these languages in the future. But currently, all of them are implemented as EST interpreters, which we will also focus on that today. And then we have also a new project called Espresso. I already mentioned it briefly before, where you can take Java bytecodes and also run it on the polyglot Truffle runtime. So you basically, we call this difference between running directly on the VM host language and running inside of Espresso, a guest language, because it's not really directly running on the host VM. And that also means, for example, that you can theoretically spawn multiple Java instances in your Java instance and so on, right? So there are some interesting use cases there. All right, but that's not what we are going to focus today. We are going to focus on Truffle today. And what is Truffle doing differently? So I already talked about this. It's doing metacompilation using Photomura projections. It adds dynamic speculation capabilities and automatic de-optimization. It does a language composition, which we also briefly cover in the end. It does tool composition, so it allows us to reuse tools for multiple languages, so not every language needs to implement its own debugger, for example. And then it allows to embed languages, for example, in the database or in an application server once, and then you get any other language as well, right? So you basically have a language agnostic API that you can use to embed languages. And then you basically can run any languages inside the box if you want. And for enterprise customers, like sandboxing is also very interesting, where you really can run untrusted code. So let's dive in. I think that is a good point for questions.
I don't see any questions in chat, but do you guys have questions? Doesn't seem to be.
All right, let's move on then. Okay. Yep.
Okay. No, someone just said not for now.
All right, so let's dive into a concrete example. That's where there was a lot of concepts here, but no real code. So here is some code. So we start. So as I said, Truffle is uses Java primarily. Actually, it uses bytecodes, but Java is the language that is closest to bytecode. So it's also the best language to write Truffle interpreters in, because you really want to control very closely what bytecodes you produce. People often ask, can I use Kotlin or can I use Scala? I think Kotlin is still close enough to Java bytecodes to would be feasible, and there is also some interoperability with Java annotations, which is needed. But Scala is really adds a lot of abstractions on top when it produces JVM bytecodes, which makes it really hard to use in this scenario. So Java is the language we're using. And so we start off with an expression class that extends node. Node is the Truffle base class for all the nodes we're using. And then you need to specify an execution signature in an EST interpreter that does EST traversal. You basically, at every node, you execute the root node, and then it traverses down and propagates down the entire expression tree. In this example, normally you would pass to the execute function a frame abstraction, something that represents the current stack, where you can push, pop, local variables and stuff like that. But for this example, in order to make the compiler graph simpler, for the later examples, I use just an integer array of arguments. So in a real interpreter, you would have a frame where you push, pop, local variables. But then it wouldn't fit on the slide, so I didn't want to do that. So the next thing is we will actually define our first operation. The simplest one you can think of is an addition, which also extends expression. It has two child fields, the left and the right node. There is this child annotation, which will become important when we step through the partial evaluation process. So you basically say, this is part of the EST, because you might also store other data in your EST, and then the framework knows which one is actually a child node and which one is not. You pass those left and right expressions in your constructor, and then the execute function, you just execute the left expression and you add it to the right expression. I think you have done a similar thing in the past, right, Niklas?
Yeah, they should have.
Yeah. Right. And then another thing is we need to have a node that actually accesses an argument. And here you have a final field for the index that is not annotated with the child because it's not part of the EST. It's just part of the operation itself. You pass the index, and then in the execute function, it does nothing else than taking the arguments and reading from the index field. And then the interpret function itself for this EST is you take an expression, you have some arguments. We already talked about this partial evaluation step, right? So that's why we're using this form. And then you just call into the root expression, you execute it and pass down the arguments. And for this example, we also need some sample program. So I use the sample program of just adding the three arguments all together. So you basically build up a simple EST for that, so taking the first, second, and adding it to the third. Right. Important to notice that normally you would take some source code and you would parse them, but Truffle really doesn't care about parsing. It gives you all the flexibility you want to have there. So you can use Antilar or some other framework where you can specify your grammar. I will quickly show you the grammar of simple language later on. Yeah, but again, Truffle doesn't care how you produce those ASTs. You just need to produce them somehow. And then the first Futamura projection comes in, right? So you have the interpreter function again with the expression and the arguments. And now we say that the expression, which is our source program, is the static input in the partial evaluation function. So you take partial evaluate of the interpret function using the sample AST, the constant values of the sample AST, and produce a function that interprets only the sample AST, right? So you have interpret sample, and the sample is now no longer changing. And what follows from that is then the compiler can do the optimizations now. So we've covered this, and in this example, if you would apply the second Futamura projection, you would partial evaluate the partial evaluate function with the execute functions of the individual nodes. But we will, yeah. So just so you understand what the second Futamura projection would be. This is the first. So the compiler now can take the sample program, the interpret sample function, and then all it needs to do is follow, right? Since sample is now a constant, it's a static input, right? We can inline the sample execute function. And since the sample was an addition, right? We just inline the addition some execute method here, right? So we end up with sample.left.execute and we plus sample.right.execute. So since sample is a constant and the left field is annotated with this special annotation called child, the compiler will also treat it as a constant. So it will read the left field as it was in the sample program, and then will also inline that. So you end up with sample.left.left, which is also an addition if you look up in the sample program. sample.left.left.execute, then sample.left.right.execute, and the third, the right execute, was actually an argument node. So this will now index into the arguments array with sample.right.index, since right was a child field and so on. So now we just need to follow this along. We basically inline the last two remaining execute methods, which were both argument access0, argument access1. And now we can also, since the sample.left.left is now a constant and index is a final field, right? So it will not change anymore. We can also fold all these index fields into the program, and we end up with the actual optimized program without interpreter dispatch in between. So this is really the first Futamura projection, and so important to note is that we of course don't generate Java code like this in the compiler, right? So this all works in the compiler intermediate representation, and this is a very optimized process. So it's not so easy to inspect what the partial evaluator exactly does step by step. But to understand it, I think it's good to see it as Java pseudocode to understand. We are actually working on tooling to make something like this possible also for existing programs. So you can see Java pseudocode for the individual steps that actually happen in the compiler, but like you need to translate the compiler back to Java code, and it's yeah, that's a bit messy. So it's but I wish we could do this.
Yeah, that would be very useful.
Yeah,
I would use it.
Yeah, I actually have a small workspace where I try to do this, and it works well for very small things. It doesn't work well for big things. So yeah, especially when you have a little bit more complex control flow, it becomes really messy.
I guess you'll show some of the graphs
yes.
later.
Yes.
So instead of looking at Java programs like this, we actually look at graphs that have all the instructions in them. So that would be interesting to see later.
Yeah. So actually 2 slides from this. All right. So you also need to have a way to initiate partial evaluation for the Truffle framework. The way this works is you basically have a root node here. The root node has a predefined execute method that you just need to override and implement. And for example, we just take the first argument and then assume it's an integer array and then pass it down our expression tree. And this is again a child annotation field, so the body execute will be inline during partial evaluation. I already talked about this, that a just-in-time compiler or a dynamic compiler calls a function first interpreted and then goes to the optimized code. And the way this works is you create this root node function here with the sample program, and you wrap it in a so-called call target, right? This is the thing that basically represents a function that you can call anywhere. And the call target implementation internally has a counter where it says, all right, when I'm called often enough, I actually will compile this function. So in the sample program here, we just call it 1,000 times, and ideally the compilation threshold is 1,000. So after the 1,000th call, this will actually get compiled. But this is not the case that we wait for this, right? So this is typically happening in the background in a compiler process, and then it's installed when it's done. And then basically, you instead of using the interpreter, so the interpreter is kind of the Java program of the same interpreter, we install the optimized machine code. All right, and long story short, let's have a quick look at this. All right, so here's the code in Eclipse. Is this readable?
Yes.
So this is exactly the same code that we have seen before. You have the expression node, that is just a Truffle node. You can look at the documentation, the execute method, the add that has the expression, the 2 child annotations. So it's really exactly the same code. And here we have the root node function, and we have the execute function. We have the main program that creates this function. So Truffle has a lot of has also an abstraction for languages that you need to implement. But to just showcase the compilation part, I skipped all that. and directly use call target. Normally you would implement a language, which we also see later on. And then we call it 1,000 times. And what I do in this demo run is I will actually disable background compilation. So we really get to see the compilation that's happening in the background. So here is the demo screen. So this is the PE demo repository that I've shown before. And I've installed Graviem there. So if we do Java version, we see this is a Java hotspot VM, version Graviem 21.1, blah, blah, blah. So, and then there is to make it a little bit simpler, second. So this will actually, this script will just add a lot of these program arguments that are typically hard to discover. Normally you would not use that if you will really build your own language. We would recommend you to actually start with our skeleton language, simple language, fork that and implement the language. But for this simple example, we need to use some arguments that I want to hide from you so you're not confused. So, so this demo one, you can just run. And it has enabled also the compilation tracing. So you will actually see what's going on in the compiler. And it says engine up done, our function that we created. The EST was 6. We disabled multi-tier compilation. So we basically have multiple tiers of compilation going on. We only use the last one here for this example. And then there is no inlining going on. There is some Growler R nodes that were produced, and we produced 358 bytes of code. And now you can just run the same one with disassemble. This is adds some additional VM arguments that show you the generated machine code. So this is the generated machine code for the function we've produced, but this is not really usable for anyone. So in practice, we never look or rarely look at the machine code unless you work on the compiler backend. But most of the time, we actually look at the compiler graphs, which you can also produce with one.dump. That will dump the graph into a different tool called the Ideal Graph Visualizer. And that Ideal Graph Visualizer now sees a new function here. It's the same function that we've seen in the debugger. Because we have dumped it, it directly was appearing here in the graph. And here we can see, first we can see the EST that was dumped. Since we annotated the EST with this child annotation, it also knows how the EST structure looks like. So you basically, you see the same add nodes and argument nodes as a tree visualization here. Yeah, it's not that useful, but yeah. And then here we see the individual compiler steps that were produced. So here we can look at the graph after partial evaluation, after some additional Truffle specific optimizations we do. Lowering, and Graal is split into 3 big tiers: the high tier, mid tier, low tier. And these are kind of different representations. I won't have time to go much into detail here. There is a lot of good material that are linked in the publications. And also Chris Seaton did a very good introduction to compiler graphs. But the very basic thing I will explain here. So this is now the produced, we have seen the Java code, and this is now the same compiler IR representation. You see here red lines and you see blue lines. The red lines is control flow. As you might remember from the example, we don't really have any control flow here because we just load the index and add them all up. So the red line is really just a straight line. And the blue lines are data flow. And this is a special Graal representation, which is also a little bit known as sea of nodes or soup of nodes sometimes. This is basically a very flexible compiler IR representation that was initially invented by Cliff Click, I think, and used in the C2 compiler in Hotspot. Quora uses a modified version of that, where certain things are fixed, like in certain phases of the compilation, like in some phases the control flow is fixed, in some phases the data flow is fixed. That simplifies writing optimizations for the representation. But then you can follow all the lines. You can highlight them to make them a little bit easier to see. The visualization focuses on showing the control flow properly, and then the data flow gets messed up a little sometimes. So it's a trade-off. But what we see here, here is the start of the program. We basically read the first index. We read the index of position 0. So if you hover that, you see index value. And an interesting feature you can actually do is, if you configure this correctly, is you can show the Java code to this. So if we click on one of these load indexed ones, we can directly jump to the Java code. So this IGV is actually based on NetBeans, and it uses the NetBeans IDE component to also show a source code. So you can actually see which parts are part of the compiler are. And if you select it here, you can directly jump to the individual load index. And here, if we select either of those, they all actually originate from this execute method, because it's just 3 different argument nodes we used for partial evaluation. And if you jump to the plus, I think we jump to the, yes, we jump here to the addition. That's nice. And here it's as well, it's also the same addition. And you can also see the full stack trace, function execute, add, where this is coming from, this addition. And this one is just one add. Does it make sense? So the gray ones, these are just constants. If there's a C, then yeah. Any questions for this?
I don't see any, but yeah, is there any question? Maybe if you want to ask a question, say that you want to ask, then you can take your time and type it. That way we immediately know if someone's interested to asking a question.
Yeah. So we talked about that we need to reconstruct the interpreter state of the to actually jump back to the interpreter program, to the Java program. So the compiler IR also keeps state nodes. We removed them here. So basically these are the green ones. We don't have too much here, but these basically say how to de-optimize back to the interpreter. And that basically keeps track of the optimizations the Graal compiler does, so we can undo them automatically. So one of the things that, yeah, I will talk about this later. Okay, then let's move on from the demo to the next part.
I have a question here.
Yes.
Isn't de-optimizing as simple as just going back to the interpreter, meaning that you already have your interpreter and you know the bytecode that's going to be interpreted?
Yes.
Or like you make it seem like you take the compiled code and apply some modifications to it? Could you clarify what's going on there?
So here, so this program is really more JIT and not dynamic compilation yet, because we don't really have any de-optimizations here, right? Because the integer array will always be an integer array, and the load index is always from a constant offset. There is nothing that can go wrong here, right? So there is no de-optimization here. So that's what actually I want to do in the next example, where I want to introduce speculation and de-optimization. So we're taking it from a JIT compiler to a dynamic compiler. So this is dynamic speculation and the optimization. So we've already talked about this. So you now have the EST. And in the dynamic compiler, you cannot just make, when something becomes hot and you compile it, you can also collect input profiling feedback and then show it in the EST. So you start off your EST nodes as uninitialized nodes without any profiling information collected. You run it in the interpreter. The first few executions will run in the interpreter because the runtime system didn't say it's hot yet, right? And then at some point, you optimize the whole process using the partial first Futamura projection. And it will just assume that all this profiling feedback becomes stable. So here, for example, we observe that this node has seen string values, so it will speculate to continue to see string values. And this node speculated to only see integer values, for example, and it will continue to optimize. So you can produce optimized specific code for only the integer operation, and here only for the string operation. And when you optimize using partial evaluation, basically the interpreter dispatch really goes away, and we produce this optimized machine code like in a normal compiler. But now what happens if one of these assumptions we've taken, for example, the input value, you need to check that you still have input values in your operation. What if that suddenly is no longer an integer value and you get a string value? What then happens is the process I called already de-optimization, and then you jump back to the interpreter program and you rewrite the EST in a way that it now can handle not just string values, but integer and string values. So you could not, for example, it would be an error to here. So there's one of the properties that we need to guarantee, which is finiteness. So the whole process, this whole loop, needs to eventually stop, right? If this doesn't stop, we call this a de-optimization loop, right? Which is actually a common problem we have to debug in our interpreters. But we're working hard on tooling to detect those things. But a common mistake would be to go from the integer case directly only to the string case here, right? If you then compile only with the string case, there might be an integer value coming around again, and then you basically enter the cycle again. And if you then rewrite only to integer values again, you will repeat this forever. And the optimization and recompilation is really, really expensive. So you should really do it rarely. That is important. Otherwise, the whole compilation doesn't pay off. And this is also where, when you see you have a runtime system and it includes compilation, and it becomes slower, right, than the original interpreter that just did interpretation. This can happen if you have one of these de-optimization loops, and that is typically considered a bug in the interpreter. But what you correctly do is you rewrite your operation to integer or string, and then recompile.
So is it fair to say that the state node, the green box from before, is basically the profile information? So it's like whether it's a string or an integer.
Yes. So the color indicates a profile, and this orangish color here is basically indicating uninitialized, no information about it, right?
When I meant green box, I meant the green box from the IGV graph. The state node.
No, yeah, no, that's not really the same thing. That is what might be a bit confusing. Yeah, no, the state nodes really just have metadata necessary for the compiler. You don't need to care about this. This is basically so you can do this operation here, right? All the information needed to do this, the optimization step. But the cool thing about Truffle, when you do the speculation and the optimization, this step is fully automatic. You don't need to specify how to reconstruct the interpreter. I know from the engineers in the hotspot team that it is really hard to do this manually. And in hotspot, this is done manually in the compiler.
Yeah, automatically, yeah. And so when you de-optimize, you do go back to the interpreter temporarily, right?
Yes, you run it for a while longer. Actually, we will try to recompile it already on the next execution of the function. There is also a thing called on-stack replacement. So sometimes you cannot just jump to the optimized code on function boundaries, but sometimes you also need to do this in loops, right? Because if a loop runs for 3 trillion iterations, you will never hit a function call boundary often enough so it's actually compiled. So you also want to compile the loop itself on its own sometimes. So we also have a mechanism for that, but I will not be able to talk about it today. Okay, so let's go through example how you can use this in Truffle. So we have a new operation, which we just the absolute operation, which takes an operand value, just a single operand, and executes the operand, and then if the value is greater or equal to 0, we are just returning the value. And if not, we return the negation. So basically, this operation always produces a positive result. So, so this is a very common operation. Most languages support it in some way. Sometimes you just write it in the language itself, but in our language here, we just have our own operation for that. And now we want to profile some information about it. For example, we want to profile that the value is always positive, right? So because if the value is always positive, we only need to care about this particular case, and we don't need to care about this particular case. So in the previous picture, this would be our integer case, and this would be our string case. So the way that you do this in Truffle, you have a new field called compilation final, the new field that is annotated with a Truffle annotation called compilation final that tells this field is part of the EST node, but you should treat it as a compilation file and fold it doing partial evaluation, right? So similar to that we have seen in the original example where we folded and execute the execution through EST nodes, we can also fold now all these partial evaluate all these access to the C negative. So we create a Boolean. Have we ever seen negative values? This is indicating, right? And if the, so basically in the execute method, if we reach that particular branch, we just say, if we have not seen negative values yet, right? We do transfer to interpreter and invalidate. This is just a very long name for de-optimization. So we de-optimize the code, jump back to the interpreter, and the interpreter will continue executing here, set the value C negative to true, and then continue executing. If we have never seen this execute method, then C negative will be false, and the entire if branch will fold. So to repeat this, if the compiler sees C negative false, then we basically get in the compiler this operation where we have value greater or equals 0, return the value, else de-optimize the code. And you really don't need to specify how this de-optimization happens. You just need to say that it happens, right? So this is the typical very complicated step, but in Truffle it's really simple by just calling this function. And then the C negative value can also be true. And if C negative is true, we basically get an operation in the compiler R that is full, right? Return value, return minus value. In a real implementation, you probably want to profile both branches, but just for simplicity, I've just profiled one branch here. And there is also in Truffle some primitives to make this a little bit simpler. There is a condition profile and a branch profile you can use, which works exactly the same way as this node. There is nothing special. It also folds through compilation final variables. So one important thing to highlight here is, why is this even desirable? Why do you would you want to do this? And the important aspect here is that this branch does basically not exist in the optimized machine code. Here, this branch exists. So here, the optimized machine code needs to branch. If the value is greater or equal to 0, return the value. And here, the optimized machine code only needs to check that the value is greater or equal to 0. And then it can assume for all the code that comes afterwards that the value is always be greater or equal to 0. And you don't need to introduce control flow. And this allows the compiler to argue about the result of this operation much better, right? For example, if there are follow-up optimizations that would depend on positive values, you know that it's already a positive value and you don't need to do anything. Yeah.
We'll talk more about that in the lectures about optimization, which I'm making currently, and should
really
be there
good.
next week.
Yeah. Very good. I would like to see the slides.
I can send you.
Yeah,
sure.
Yeah. Right. Okay. Right. So the important thing is we add this compilation final annotation. You must not modify this local field at arbitrary places. You are only allowed to modify the field after transfer to interpret and validate. In other words, you're only allowed to modify it when you're running in the interpreter mode and not in the optimized mode. Yeah, otherwise the compiler will not see that this value is changed and it doesn't know when to recompile the code. So we also call this internal invalidation, because or internal speculation is because we actually check the value is always greater or equal to 0. There is also external invalidation, which I will come later on, when you cannot really, the invalidation depends on a more global aspect of the program, but I will explain that. Right, so second demo. Demo 2. All right, here, the same code, expression, execute, absolute number, expression, execute. Oh, here actually I modified the code. Let me quickly clean this up. Don't need that. Here actually, what was here before I was rewrote this to the Truffle primitive, because in the previous presentation that was a question. So we do this in negative, transfer to interpret and validate. It's in a class called compiler directives. We have an argument and we have a function again. And so here the program is really simple. We just take the absolute value from the first argument. So we create the sample program function absolute argument 0. We create the call target again. And now to indicate, to actually test the speculation, we first call it 1000 times with positive values, and then we call it 1000 times with negative values. And what now should happen is, like, the function is called 1000 times with only positive values. So the compiler will actually leverage this fact that the C negative Boolean is false, and basically produce a de-optimization for this branch. And as soon as we call it with the negative value, we should see an invalidation of the optimized code, and then a recompilation, because we call it often enough. Actually, I think calling it once or twice should be enough here to compile it again. Okay, let's see whether demo 2 actually does that. I also enabled additional tracing. So you can enable trace, transfer to interpret and validate. So you get this additional information when de-optimization happens. So here we have the function. It has 349 bytes in the compiled mode, and we see that a de-optimization happened here opt invalidate function, and we see a recompilation, and we see that we have a new function compiled here, which actually is funny that this has actually a slightly smaller size. It's because this one includes the de-optimization. This does no longer include the de-optimization part. I think that's the reason for the difference.
Yeah,
right.
Typically the branch is more than just flipping the sign of a number. Like, there's typically more operations there, so it would typically be smaller.
Yeah. So then we can dump this to IGV. Now we have a new dump. Let's close this. And we have two dumps, the first function compilation, the second function compilation. In the first one, we can again look at the graph. And now you see that it actually, let's also click on this so we can see the code, yes. So here we see we load from an index 0. And we load the argument 0 here. This is the load indexed from the frame, so you can just ignore that. That's not important. And then what we do is basically the compiler transformed this into a guard, which will say that which is greater or equal 0. If you look at the code, this is the guard that was produced by this condition. And then it will know how to de-optimize. And if we show the state, we don't see the state here because it's disabled in that Graviem version. I would need to run in a different mode. So yeah, we cannot see that at the moment, but it doesn't matter. But then you jump to this transfer to interpreter. So this is the guard And for the second compilation, we would expect now to actually see some control flow. And that's what we see. We move this state again. Again, follow the red lines. Means we are following the contour flow. Now we actually have a contour flow split here, and then we have a contour flow merge here. And you can already see that this is more complicated to execute and to argue for a compiler. So every value that now needs to go through this if condition, afterwards you need to the compiler needs to see that it's either this value where we didn't go through this branch, or we have gone through this branch, and the compiler uses a phi node to represent this. So yeah.
We'll also briefly explain what a phi node is in the optimization videos.
Very good. So
yeah, because it can be tricky.
Yeah, and especially when you add loops. So we can also follow quickly, I think, the individual compiler stages. I think in the first ones, there's nothing happening. Here, yeah, there's nothing really happening here for this trivial program. But now we can see in after the height here, we already transformed the high-level Java operations in array reads, and then doing some Java operations for compression and uncompression. And you can follow along here. After mid here, this becomes even lower level. So we now read from offset addresses. There's memory anchors to implement the Java memory model. And then we have an allocation for a new integer, because the integer in the end of the program will be actually needs an allocation. If you do calls from a truffle function to a truffle function, this allocation would go away. It's only for the root function invocation that we need this. Right. And then there is also a truffle save point added. That's a rather new thing. Yeah, so won't have time to go into much detail, but you see it becomes lower and lower. And here we now have the if condition of the guard materialized again. So we have now a condition for the guard. And here you can see deopt. Right, that's the wrong deopt, I think.
As you can see, that's a lot of complexity for just taking the absolute value of a number, right?
Well, there is a lot about this allocation of the integer in the end, so you basically need to stop reading after here. So it is not that bad, but there's a lot of complexity to handle all these de-optimization cases, and there is a lot of opportunity to do this the wrong way. Yeah. And the important thing here with Truffle, you don't really need to repeat this step for every language you implement, because we always leverage this de-optimization mechanism we already implemented with Truffle that is based on top of the Java de-optimization mechanism. So yeah, and I think Java is really the top of the art when it comes to de-optimization.
Yeah.
Yeah. Right. Any questions here?
Oh, chat is still peaceful.
That's good. Tranquility. Let's move on to the presentation so you can actually see this. All right, and then there is external invalidation. I already talked about this. So what happens if you have some global aspect that you need to track? For example, in a lot of languages, it's possible to do operator redefinition, right? So for example, you could say my addition, I can globally redefine addition to call into a function, right? What you can use then for this purpose is you can use assumptions. Assumptions are basically Booleans that go from false to true, right? So in this case, I would just say, in order to produce good code for the compiler, I would just globally assume the add was not redefined, because if it would be redefined, I would need to do a function call here, which would be really complicated, right? For produce complicated code at least. And so I can use this global assumption, add is not defined, is valid. And then I just do a normal add. And if that doesn't work out, we have to use the complex code. So if this assumption happens to be true or stay true, assumption always starts in the state true, then we can just fold this entire condition, and this code afterwards just becomes that code and gets eliminated. So we really just have the add. because assumptions can be folded without cost. So the way this works is, and that is the interesting thing here, is when instead of actually producing a check where you read the current state of the assumption in the compile code, the compiler will register the compile code into the assumption. So the assumption knows which compile codes it needs to invalidate if I'm becoming false or if I'm invalidated, right? So in this case, we have the defined function that we defined with a string name and a function. And if the name happens to be plus, then we say, all right, now we have a global redefined function. Now we can no longer use this optimistic assumption, and we need to globally validate that. So again, the compiler basically sees this assumption as true, then it registers the code as in the assumption. If the assumption is no longer true, it will not register the code in the assumption. And the compiler invalidates all the code that is in the assumption when you call the invalidate function. This sounds trivial, but it's not. So doing this, especially for multi-threaded execution, is quite tricky because you have code that is currently executing in parallel and things like that. So it's also something you don't want to do manually. And Truffle also provides a way to just do this kind of optimizations without big hassle. So
yeah,
yep.
And this is very useful for dynamic languages like Ruby, where basically you can redefine a lot of things. In Ruby, it's really chaotic. You can redefine anything at any point. And so in order to have good performance, we like to make assumptions that things are not redefined so that the code can be fast. And then in the rare case where we actually redefine, then we invalidate the assumption.
Yes.
So it's a very great tool.
Yeah, you have typically also multiple levels of assumptions. You start like, oh, my program is always executed single-threaded. That's one of the assumptions, right? Yeah, well, you could in theory do, I only have seen positive values globally, right? Then you don't even need to do the check for the positive value, right? Because if you know you only have positive values in your program, you don't need to check for them, right?
I'm not sure how realistic that one is, but
yeah,
definitely for like function redefinition, that one is
yeah.
used in practice.
So this is the art of writing a Truffle interpreter. It's really finding the right balance here. What is too aggressive and what is not aggressive enough, right?
Mm-hmm.
To produce good code. So you should first, it should be so it should actually not be it should be an assumption that most of the time stays true, right? So otherwise it is wasted effort, right? Because if the assumption happens to be false, you pay the cost of the optimization, which is extremely expensive, right? And that should really not only happen at most once for a function, ideally. And then you should become stable. Yes. Okay. So the next concept I want to touch is boundaries, partial evaluation boundaries. The partial evaluation, you've seen that it's very aggressive in inlining the constants, the child nodes, and then constant propagation. What would happen if you would introduce a recursion there, for example? You call the same function again, right? It would basically inline that function, inline that function, inline that function, and we'll do that forever until it bails out. In order to have this kind of more complicated code that is hard to partially evaluate, Truffle has a thing called Truffle Boundary, where you can do things like hash map lookups. Non-intuitively, the Java hash map implementation actually has a recursion in the get method. So if you would use this in partially evaluated code, it would go into the get implementation, try to partially evaluate that function. And that function is really not designed for partial evaluation, right? So we have this notion that the code you execute really needs to be also designed for it. So we have this Truffle boundary, which basically will stop here and then stop partial evaluation here and then just produce a runtime call, so an invoke instead of doing this in the compiler graph. Yeah, but right, this is, for example, use this for all the functions that are not designed for partial evaluation. Sometimes you need to call into code that you don't really control, right? So you don't know whether it's valid for partial evaluation. So then you need to kind of do that. You should be rather conservative here. So even if it's currently partial evaluatable, it might not be so in the future by just having an update in the library, and then you get bad errors. Or if the logic is really difficult to partial evaluate, some recursions that are infinite, actually we can partial evaluate. And then rarely executed complex runtime routines, I already mentioned that. So this results in an evoke node in the GraalIR in IGV. And this is typically the first optimization goal for a Truffle language implementation, to get rid of to have as few boundaries as possible, because these boundary calls are expensive. The compiler cannot argue across it. So basically everything that is behind the Truffle boundary will be handled as if it would be interpreted, right? So you don't get any benefits from the Truffle compilation mechanisms anymore. So I will show this one example, because people typically add trace output in their interpreters, and then they just do system out println. And what happens if you do that is you basically get this kind of graph, a huge graph that is with a lot of boundary calls that is really slow. And it's much slower to actually partial evaluate this and produce the optimized machine code with system out println than it is to just call this with a Truffle boundary. So how are we time-wise?
You have 35 minutes left, something like that. Yeah.
All right, so we'll need to skip a few parts, but okay. So another important thing you need to understand when you implement a Truffle language is inline caches. And I want to show this with the example of a polymorphic of a function inline cache. Inline caches you can do for all kinds of speculations, but here just focus on functions. So this means, so if you have, this is JavaScript code, so you have a function foo, and you call this function directly, right? There's just one target for this function. It's not redefined. There is no, we know that we always need to call foo. So we call this call side monomorphic, right? So because mono for one and morphic for transformation. And so here we know it's foo. But what if we basically could have multiple function targets at a particular call site? For example, you have an array of functions, foo, bar, bus, and you iterate over those functions and you call them all at the same place here. So this function call can then be either foo, bar, or bus, right? And then there is the worst case where it's just like way too many, like 1,000 or here 10, but 1,000 entries of functions, and you would not be able to call them. And this is a pattern you want to optimize in your language implementation. And the way you do this is you record which functions you have seen at a particular call site, and then you build up a chain of functions that you then call. If you record the functions, so if you profile the functions that you're executing, this allows us to know which potential targets could there be at this call site, which allows the compiler as a follow-up to inline those calls. All right, so in the Truffle nodes, this looks kind of like this. You have an invoke node, and you have the first entry. You start off with an uninitialized node that would just de-optimize. On the first execution, look up the function, create a new cache entry, and then invoke the function. So in the first call, we would just keep track of the first function. So we basically build a singly linked list of all those functions, and always chain in the end with this uninitialized entry if you see a new function, right? So again, this is a compilation final entry, right? So in the execute function, we just say, is this object still of the same shape? Then we can just execute the function directly, because we know for this object shape, the function does never change. Then we just call next execute for the next chain entry, right? The next chain entry might just be an uninitialized entry that transfers to interpreter, de-optimizes again, or it might be another cache entry. So this way you basically can chain multiple values that you record in a single chained list. So here, in the case of two functions, you basically have an invoke, then a cache entry and another cache entry. In the end, you have the de-optimization that jumps back to the interpreter if you see a function that we haven't seen. Then we talked about the megamorphic case, where you actually just have too many functions, and at some point you just cannot keep track of them anymore. So you would need to go here. We just go if anything greater than 2 functions. The amount of functions you typically profile is kind of the magic optimization number in a lot of language implementations. I think in JavaScript it's currently 8. In Java it's currently 8. I think in JavaScript we increased it recently. I don't know. It's really hard to determine a good number for this, but yeah. And then in the generic case, we would just call the function behind a boundary or with an indirect call. So it's important to understand this kind of inline caching, because this allows you to cache and chain multiple values that you observe.
Just a question clarification, because I'm not sure to know what the shape is.
Yeah, yeah. That these are quite kind of old slides. So the shape is the structure of an object. So if you create an object in the dynamic language, then you don't know which class. I mean, you don't necessarily know what structure that object is going to have, because dynamic languages often allow you to redefine and define new variables in that object. And every time you define, or not assign, but define a new variable in your object, in your class, right? The shape changes. Basically, the amount of fields that you need to represent this object changes, right? And you can also, whenever a function is redefined for a class, you can do a shape transition. So a typical language implementation gets a tree of these shapes. Other language implementations call this hidden classes. So this is really essential to optimize dynamic language implementations. But it's not really too important here, because it's just some condition. You just see this as some condition under which we can assume that the target is still the same, right?
Yeah, the function being called is the same. Yeah, exactly.
Yeah. You can do any other condition here. You can check whether the shape is the same, or which we will see in a second, which if the language of the object is still the same, right? So the original language, if you compose multiple languages, for example. Okay, and this is complicated to implement. So here is where my master thesis comes in. I did this master thesis to actually make this easier to write this kind of inline caches and specializations. If you look at the Truffle code, most of them you will see this specialization annotation that allows you to write this chaining representation. Here, for example, we have the limit, we have 2, we have the cached value, that is the shape, and these are the cached fields that would be stored in the cached entry here. And then we have a target invoke if the shape is still the same. And here we have the generic, which says replaces do cache. So basically all those specializations, when they got activated, get removed when this one is triggered. And we can just do the generic invoke.
So yes, I feel like this could use some more.
Yeah, and we that's another lecture. But it's I actually show you some simple nodes in simple language.
Excellent.
Yeah. So so a second. So we have simple language here. Now what kind of nodes I want to show? Yes. So simple language is really simple. It doesn't have syntax highlighting in Eclipse because it's our own language. It is really just a very mixture of Java and some dynamic language. It is not a complete language. It has a lot of bugs. Its whole purpose is to show Truffle features. So it's not a real language to use. And don't use it for anything, please. So it has a main function just like Java, and you can define variables as you like them. You don't need to type them because it's a dynamic language. And here you can just iterate over just loop. You can add the numbers and return the sum. So it's a very basic language. So the way the first node I want to show here that is relevant, or the first thing, so I want to show you quickly. So in the background, there is this simple language grammar, right? So this just uses until, and in the background then produces these truffle nodes. So I said, again, we don't really have an opinion how you do this. You can choose the tool of your choice here. And if we look into the language, so the simple language, this is a way. It's also, there's a lot of documentation. You want to check it out. So what you do is, if you implement your own Truffle language, you implement this Truffle language class. And what you need to implement first is actually not this, but the parse function. The parse function takes the parse. So, and the parsing request contains a source, and that source contains the characters of the code that you parse. And here we just call into the parser, and that produces a call target. And that call, actually that produces a set of functions. But in that set of function, we take out the main function, and then we just return that as the main function. And so this is, I will just want to show you how all these pieces fit together. How you get from a simple language source code to the actual call target that gets executed. And then we have this root node of simple language that works very similar to the root node we've just observed.
Can you hear me again?
Yes, but it's the sound
Better
quality
now?
drops dramatically.
Better now?
Go again. Yeah, better.
Yeah, sorry, the battery of my, I talk too much. Right, or maybe the microphone wanted to tell me it doesn't want to listen to me anymore. So, the first thing I want to show from this example is how the plus is implemented here, and add node. And here you see the specializations of the individual values, and here's where the DSL makes it easier to do this kind of specializations I was showing on the slide for long values and for string values, right? So here you can just say specialization, then you define your add for long values, and the DSL will basically automatically check, oh, this is a long type and I can use this specialization, or the long value is actually a big number, right? Simple language supports arbitrary big numbers, but you don't want to always use, for example, the big number representation for the number, because that's very expensive. If the number is small enough, you actually want to use a long, a primitive long for that. And this allows you to basically have an operation, only for long, and only if this thing overflows, we actually rewrite to the big number version, which allocates a new object and is much, much more expensive. And it also here is behind the Truffle boundary. So we want to use this as much as possible. Then simple language also supports string values. So you also can add up string values. Yeah, and there's also this fallback annotation that allows you to define something like a type error. Yeah. Then not all your nodes are going to be DSL nodes like this with specializations. So there is also control flow, and control flow basically is the SL if node. So if the guest language code contains an if condition, then it produces such an if node, and the if node has an expression condition. It has a statement for the then part. It has a statement for the else part, which can also be null, I think. And in the execute implementation, all we do is we evaluate the condition, and if the condition is true, we execute the then part and the else part. And the partial evaluation here works exactly as the same as before. We just check that condition, and then we inline these execute void methods for these functions, and everything becomes an optimized program. But here we use a condition profile. This condition profile you can create here, and that actually creates a counting condition profile that tells the compiler underneath how many times was this function actually called, or in other words, it computes the frequency, how likely it is, or the probability how likely it is that this branch is taken or that this branch is taken. And this allows the compiler to extract out the common parts. Can you still hear me?
Yeah.
Yeah. Yeah.
What do you mean extract the common parts?
Sorry, common parts, the frequent parts, right? So what you want in optimizing compiler is you just push up all the frequent parts to the top of the function, right? So there is good locality for that code. And then you keep the unfrequent parts below that, or it also informs the inlining heuristic which functions to inline, right? The guest language function calls to inline and which ones not, right? Because you always have a limited budget for inlining. You cannot make the compiler graph arbitrarily big for huge applications. Okay. So that's all I want to show from simple language. So this is all on GitHub. You can check it out there. Yeah, how much time do you have?
About 20 minutes.
Okay. What do I do?
What do you have left in store?
Yeah, I have. Yeah, so probably we'll talk a little bit about this Tower of Babel, which is a little bit a lighter topic because we've seen a lot of code now. So we have this idea to build a polyglot VM, and recently did a presentation which I called Towards the Tower of Babel. And not everyone knows the story of the Tower of Babel, so let me quickly summarize it for you and your entertainment. So the Bible tells the story of a group of people heading east to build a city where all people speak just a single holy language. And the legend goes that they are not just building a city, but also a tower, the Tower of Babel. The top of this tower was so impressively high up, almost as high to reach heaven. So one day, this God came down to the people and looked at the city and the tower, and he didn't like what he saw, right? So he thought, when they can build such a big tower so high, they won't need me anymore. So he decided to confuse all the people and introduce, make all languages, all people speak different languages, so they can no longer understand each other. So this basically quickly brought the construction of the tower to a halt, and everyone got confused. So confused, in fact, so this language has spread all over the world. So I think, and you know what I'm going here, if you want to build a Tower of Babel, we can only continue construction if you can make these languages compose well together and work together. So if you want to really build this big, colossal things, yeah. So this is really about how can we construct such a tower. So, well, you could also say, why can't there be just this one big programming language that rules them all? Why can't we agree on a single language? So this question was actually asked on Stack Overflow, and the moderator said it's not a constructive question. I think it is a constructive question, but the problem is that people in practice will never be happy with a single language. And also you want to have some certain diversity. Languages need to evolve in different speeds. So while I can imagine there will be a future where there is just this one programming language that fits all the use cases, we are nowhere close to getting there. So to stay realistic, we need to deal with this problem. So if there cannot be that single programming language, maybe there can be a single polyglot virtual machine. So to say a polyglot virtual machine to rule them all. It's actually the name of one of our papers, one VM to rule them all. But first we need to establish why I think this is a good idea. So the first thing is feature parity between languages. When you think of a problem, you should not think of it as a single application. You should think of it as a set of applications that is needed by your project. So think of the Tower of Babel as a set of applications, not just a single application to build. So for example, if you work in IT and you need to make a decision, you will in fact use multiple languages. So if you're a big enough project, you end up with 5 different programming languages with different use cases and capabilities. They all use different tools, so you're really restricted in the choices how you can make those things, because that one language really has that that one feature, the other one doesn't. So the one is debuggable, the other one doesn't. So the one is more suitable for that case. So by having all the languages similarly efficient and supported by all tooling, we can allow that developers choose more freely which language to use, because they are all debuggable with the same thing. They all perform similarly efficient. And sometimes when a language becomes mature and actually fast enough and the tooling is really good, it typically happens that people are unhappy with the language and move on to a different one, so it's obsolete, and then we will start all over again, right? So why? So again, ultimately we want to choose the right language for the task, but we don't want to start over all over all the time. So we really want to reuse across those VM implementations. So one example is, for example, you can leverage all that work that has been done for Java garbage collectors, right? It's a lot of work to implement garbage collectors, and you really don't want to reuse. Same for the compiler, the de-optimization mechanism I talked about. You don't want to re-implement that. So this gives us a lot more flexible for this language implementations. So in a polyglot VM, runtime system in GC should all be shareable. Then the next thing is reuse across ecosystems. We have all these bubbles, the Java ecosystems, the Ruby ecosystems, all these ecosystems that write amazing libraries and tools that have different capabilities and features. So one library is good for plotting, like R is really good for plotting, but Java doesn't have that well of capabilities yet. One other language is good for complex number generation crunching, for example, right? And it would really be great if these libraries could just be shared across those ecosystems. So we don't repeat the same thing. So a true polyglot VM allows to share that. So what important to say is we don't want to encourage that you use multiple languages, right? So using multiple languages still means that you increase complexity and language. People actually need to understand multiple languages, which is not feasible in general, because I personally can only understand 2 or 3 languages at once, really deeply, and the other ones maybe roughly, right? So there will always be other people. So if you work in a team, you should still try to use the same programming language to make communication easier. But it's just a thing that was not possible before, and that should be enabled by a polyglot VM. And then you also want to reuse across embeddings. I briefly talked in the beginning about databases and how we embed there. We want to, database embedding is very complicated program for runtime. And we don't want to repeat that for every programming language. So our goal is to bring all the programming languages into the database. So so you want to reuse those embeddings. So we have a polyglot API for that. And last but not least, we have learned from JavaScript, C, and Java that multiple language implementations actually are beneficial to language ecosystems, because that requires them to build a language specification, specify features, be precise with dependencies on the environment, and the polyglot VMs benefits a lot from language specification. And we really want to encourage languages to do that, because if you start having multiple implementations, you need to agree on certain behavior. So what we currently have to deal with most of the time is, for example, in Ruby, there's only a reference implementation and no reader specification. I think there are some efforts to change that, but at the moment, I think that's still the case. And then we need to use the reference implementation as a specification for our implementation, which means that we don't know what is actually specified and what is unspecified behavior, right? So this is really hard to differentiate. So yeah, so I think good reasons to build a polyglot VM. Quickly, how you can think of how to compose languages. For example, here you have a Java type, big integer. We pass it on to a node function that produces, registers a function handler. In that function handler, you take the Java big integer and use it to compute some value. And then you evaluate everything in R and produce a nice plot out of it. And you can just pass all the values in between. And then normally you would, of course, use different files for different languages, but in this example, just to put it on the slide. There is a lot of more examples if you're interested in that, on how we do that, but I will dive in a little bit how this works, because we were talking about inline caching, right? And this works very similar to inline caching. Just now we don't cache on the shape, but now we cache on the language, right? So if you, for example, have this dot operator, this dot operator is basically a member access of object in JavaScript. And then what if this object of JavaScript is not actually a JavaScript object, right? And then JavaScript can implement it in a way that it's not JavaScript, then we create an interrupt read node. And that interrupt read node performs a thing called message resolution that then basically produces a Python operation for that read node. So it turns out the interrupt read node found out that this object is actually a Python object. It will speculate that it will continue to be a Python object in this code. So it inserts a Python read. And this is really the same as the inline cache. So if you have multiple languages, you just maintain multiple languages after each other. You might imagine it's not so easy to map your language semantics to these interrupt semantics. So we developed this interrupt protocol where you can say what in your language is a null, what is a string. So interrupt really consists of two parts. One is the mapping of the current language to the interrupt semantics of the interrupt semantics, and then how are interrupt values be interpreted in your language. So it's typically the bigger effort to interpret interrupt values than to expose interrupt values of your current language, because the surface of a language implementation is much bigger. So, but there's one fundamental goal. What we want to achieve here with this interrupt protocol is, and this is our guiding principle, we want to make code more portable across languages. So you should really develop your language, your code in the one language you have, and you have another guy who implements a different function, and you should be able to call that other function without knowing the other language. So this is really the fundamental principle we're trying to achieve here. There is, like, we constantly improving this API with new languages. We need new capabilities. Recently, we added buffer elements, hash elements. So you can pass in a Java hash map, and it looks like a Ruby hash map, and so on underneath, without the user need to know anything. Right, we have some tools. Here you have a debugger, so you can basically also debug tools, multiple tools together. This is a screenshot of the Chrome inspector that we support. And you can inspect the values there. And the way this works is using the EST nodes we already talked about. So we use a technique called node tagging. For example, if you have this sample JavaScript program and you build an EST out of it with this foo, all we require language implementation to do is you need to tag the individual nodes. So, for example, this is a root. This is a function, basically. This node represents a statement and that expression in the language, and we have certain expressions as well in the language to do that. And the way the language typically does that is by implementing the instrumentable node. And the tooling can then, independent of the language, basically insert code before or after a statement, right? And this way we can implement stepping. Interestingly, to implement a simple debugger, you don't need much more information than the statement. You need to know how the scopes are structured, and there are some more advanced APIs, but the basic thing you get by just implementing this node tagging. There's, of course, a lot more tooling. We'll list them now. Then this is how...
Just to emphasize, this debugging thing is really cool because it means that if you have a polyglot program with, I don't know, JavaScript calling Python, etc., you can have a single debugger and you can step through the JavaScript, but also the Python seamlessly in the same debugger. So that's almost magic when you see it.
Yeah, you also sample across. Like you see, if you use multiple language, your CPU sampler shows exactly which parts are important to optimize, right? Across language boundaries.
So a sampler, for those who don't know, is like a performance profiler, basically, that tells you where the program spends the time.
Yeah. Right, and this is also very briefly an API that we've built to embed languages without knowing the language. You can see the language actually is a string here, right? And so you basically create a thing called context, and then you evaluate values in strings, sources inside of that context. And this just works the same way for R, Ruby, Python. You can basically do the same thing, and you just put a different language in there. And also within a context, the guest code can access other languages and things like that. And you can fully control what privileges that context gets, what files it can access, and things like that. So you can do things like sandboxing. I already talked about all these languages we are implementing. There is a lot of cool stuff going on. There's also externally developed languages, Truffle, a Squeak implementation, a simple object machine, Yona, which is actually is a reference implementation. I think this is outdated. I need to add 2 more. there's an up-to-date list here. Yeah, I need to speed up a little. So yeah, we're going to be fast. This is just some expectations you can have. Memory footprint is one of the things we really need to optimize in the future. Also, warm-up speed, we are working very much. So I already talked a bit about that. We do multi-tier compilation and things like that. But I want to show you this because that's cool. Clear this. So what I got here is I've installed Graviem, and so I have a JavaScript executable here. So JavaScript, Graviem, JavaScript, Graviem Enterprise Edition. So now the performance is going to be bad because I'm running with screen sharing on, so hope it's not too bad. So we just take a simple program in JavaScript, and this is the program. So which is a sum loop. So you basically have for each a sum loop, and then we just steadily increase the number of loop iterations we're doing there. And instead of we're doing a function call here, so this should inline into that loop, and we should get the result of that sum. It's really just a small macro benchmark to show what compilation actually can do. So now if we run this, actually, I think I want to run this without compilation first. So here we just disable compilation. We need to enable experimental options. It takes around a second. And if we actually run with compilation, oh, it's faster. And if we enable compilation tracing, you would see that this function gets compiled and so on. So it's actually, yeah, it's not really stable with the screen sharing in background. Right. So now we can take this program and we just increase the iteration times. So you need to just double the loop here, which means that also the sum loop runs for a much longer time. Right. So if we run this again in the interpreter, it took 3 seconds because we did much more iterations of the loop here. And if you run this with compilation enabled, we basically optimize the whole thing again away. And in fact, Graviem vectorizes the inner loop here and produces really efficient code. So that's that.
Is it able to optimize everything away, or it just vectorize? It still
no,
runs
it's not.
the loop?
No, I think I verified it's not. It's really vectorization. But I mean, you need to see in the interpreter, we basically need to do the call every time, right? And in the optimized code, we just have vectorized instructions for this loop here, right? For these 4,000 instructions. So it's really, really fast. The interpreter, you have like a gazillion of Java calls in between the interpreter nodes and so on, right? And then it does also if you would have multiple loops, it would even do optimizations across multiple loops and merging and stuff like that. Everything advanced optimizing compiler does. Okay, so much for the demo. I could show a lot more, but there's just no time.
Sound is really bad suddenly.
Oh, again, better?
No.
Wait a second. It's better now?
Ah.
Yeah.
Apparently it's on my side, so please
oh,
continue.
Okay. Yeah. So we currently have a Graviem internship program that actually ends submission date. That's the submission deadline today. But I asked if you apply, we will keep it open for at least 2 weeks longer. So if you're interested in that internship program, just go ahead and apply if you're interested in what we're doing here. We have like a gazillion of possible research areas. If you're like, you can directly work on the compiler, you can reduce compilation time. We You can also work on garbage collectors in the Graviem native image tool. You can work on the WebAssembly backend, for example. You can work directly on Truffle with me. You can investigate compilation queuing heuristics. You can work on the language implementations, Python, Ruby, JavaScript, if you're a really big fan of a language. You can work on tooling. You build the next tooling that works across multiple languages. Work on our LLVM runtime. You can also work on the Micronaut framework that we are building as part of Graviem. So lots of opportunities here, a lot of cool projects. So hit us up on this website, and if for some reason in a month or two you think you still want to do an internship, you just ping me on my Oracle email address. I can help you get in touch with the right people. That pretty much concludes the thing, lecture.
Well, thank you very much. Personally, I think it was a fantastic lecture. Everything I wanted the students to hear about. So, so do you guys have any question about the presentation? It can be about Truffle, Graal in general. Ask Christian about opinions on things. You know, like usual, don't be shy.
You can also make a comment if this was new to you or something like this. It's also fine.
Yeah, a comment or some feedback. And it will be a good lead to the optimization videos that I will release. There's a lot of things that we covered there that students might think, oh yes, Christian talked about this. Okay, there doesn't seem to be. Nobody has any questions. Come on, guys.
That's fine.
Maybe it was an excellent presentation, and
no, it's a lot of new concepts typically. I will share the slides because there are a few links, so I will send it to Nicholas, and he will probably distribute them to you.
Yeah. So, there's a drive with all the slides, so I will put it there with everything else, and I'll upload the video to YouTube as well. Okay, well, if you guys have any questions that comes to you afterwards, you can always send them to me and I will forward them to Christian. So that's also an option.
Yeah, so also on the Graviem website, we have community channels. If you're independently just to engage with the Graviem community, we have a Slack channel there. We are really active. So if you want to take this first spin and you get stuck somewhere, feel free to just ask the community there. They will be helpful. You can also directly ask me. I'm also available there almost all of the time.
It's very reactive. So we have some comments coming in. So Jeff Aru asks, I don't really get how you manage to recognize different languages. So I think maybe if you go to the slides, the one when you have this JavaScript example with R and Java, that could be useful.
A sec.
And Jeff will tell us if that's what he means.
This one, or no? I think the.
Yeah, I would have.
Yeah. So I think it's good to explain it here, right? So for example, here we create a Java type big integer, right? And here we call a function on that Java type, right? The way this works is the language first checks, is this a type of my own language, right? And if it's not,
something. This is all JavaScript code, first of all, because I think there might be a confusion that there's some parsing of multiple things happening, and this is all JavaScript code.
This is all JavaScript.
Yeah.
And you basically take this big integer value, and this is not a JavaScript type. So the language implementation, the Graal JavaScript language implementation, will ask this value, how can I invoke a function on it? And it will provide a node that specifies how to provide. And the JavaScript GraalJS will just insert that node here. It doesn't know which language it is, right? And that node includes a check that this type is now a Java type, right? So we have a guard. This is a Java type. Call this function, and we call this function. This all works the same. It always does the first time it's executed, the first time it's invoked. We will look up the language and then insert the proper nodes. And then we make the assumption that we have previously seen Java values here, so we will see them in the future, and then we de-optimize if it's not. Did this answer the question?
Well, Jafaro, does this answer the question? Well, yeah, one other thing we can say is that, okay, it says yes.
Okay.
Yes, yeah. So yeah, really, like you make a normal JavaScript call, like value of, but the runtime knows that big integer is not a JavaScript value, and so it will forward that value of call to Java, actually.
Yeah. Yeah, but
and
it will not just forward it, will actually insert a node. That's important because then the partial evaluation can kick in and optimize the languages together in one compilation unit.
Yeah, so there's no boundary between them.
Yeah,
it's all the same program. Yes, exactly. And so Martin gives a comment. He says, it was really interesting. I wasn't aware of the back and forth with the interpreter compilation. So the optimization, that's a new concept.
Yeah, and it's a complicated concept. The reason many language implementations don't do it because it's very, very complicated to do manually. And this is really where the major innovation of Truffle comes in with applying this Futamura projection, right? In the 80s, this was just a theoretical concept and it was not really really applied, but now we try to apply it. We have our problems with it too, like compilation time, really something we need to work on. There is actually a second project that uses Metacompilation, which is called PyPy. If you're familiar with the Python ecosystem, you probably know that project. They use also Metacompilation. They also have a proper implementation of the second Futamura projection already, which is really cool. So they have faster compilation times currently as we have. But what they are using a trace-based compilation technique. And trace-based compilation techniques has its own issues, and they also have their warm-up issues. So so both approaches currently have still their downsides. But in terms of peak performance, I think we are a bit better because Graal is a more mature compiler and does more optimizations.
So those are the only two projects that do this kind of partial evaluation, Futamura projection.
Yeah, for real. Yeah, I mean there are like research prototypes and stuff, but these are the real systems you can use for a system.
Bleeding edge stuff.
Yes.
All bleeding edge.
Well, for me, it's there for almost 8 years now, so it's old stuff for me.
So Stanislas asks, how does it handle if big integer is an object in two different languages? Is there a clash of language? How does it select the right one?
No, here you need to select the language, right? So here we say Java type, right? So this selects the language, and here we say R, right? So this is basically, you need to know which language you're looking up the type from. But if you have any value here, right? So you can just change this to R type lookup or a Ruby type lookup, and then the methods work just the same way. It just needs to have a static method defined value of and a pow, and then the code would just work.
Yeah. So the left big integer is just a JavaScript variable, but you do the lookup via Java type, and that tells you the Java, of course.
Yeah. I mean, if you just pass, you don't need to use big integer. You can just assume this is any number, right? Then you can just use the JavaScript plus operator directly on the Ruby number. That will also work. So it's not just that we can call functions of others. We can apply number arithmetic. We can interpret strings. We can interpret hash maps, as I talked, buffers. I think we have the full protocol here, right? Functions, executables, instantiables, whether something has a meta object is handled currently, where it's declared, that it's iterable, hash I already talked, buffer, and then we have types, whether something is null, string, boolean, and this is, you map your language to those types, and then the other languages will be able to interpret it, your languages using these types. So it is an intermediate language. You only need to do this. So one of the problems you have with language interop is that you get in an n squared problem, right? So you basically need to do interop between each language individually, right? in each language combination. And that would just be unfeasible when the number of language grows, because you would so have so many interoperability protocols. So the only real way that you can do this is by mapping it to a language in between that all the languages agree on. And that is our interoperability protocol. That is not that is not perfect. That is best effort. Again, the goal is to make code portable across languages, to make it reusable. Not all the code, but most of the code.
Yes, that's quite useful, because the normal approach would be like to, I don't know, wrap a library, and then the library gives you a map or a dictionary back. But if it's a dictionary for the foreign language, you cannot do much with it. You can't pass it as a dictionary in your language. But with the interop protocol, you can do that. And that's where it's really, really fancy.
Well, it actually doesn't need to be that fancy. Like, just parsing strings from one language to another is horrible. It's really, really complicated, because string formats are very different between the languages. And in Graviem, it's just you pass the string. That's it. There's no conversion between. The language implementation takes care about the conversions, and if needed. Ideally, it doesn't convert because it uses the same string representation.
Yeah. All right, there's no more questions. So yeah, thank you again. It was very instructive. And yeah, so if in the future you have any questions or interest in Truffle, Growl, don't hesitate to go to the Slack channel. And there you have it.
All right. Cool.
We have some more thank you in the chat. Very interesting presentation. You even get a thank you, sir. So all right.
Thank you for listening, sir.
Yeah, well, I'll see you all next time. For my students, tomorrow we'll have a lab session where you can come and ask questions about the project. We're doing that. So see you all tomorrow, and Christian, see you later.
See you later. Bye.
Thank you very much.